Hey all, welcome back to Circles. This will be, let's see, section 10.1 now. So we're starting chapter 10 and we're starting section 1. And so 9.2 was the start of learning about circles. The section title for this is The Circle. Makes me laugh a little bit. So a lot of the information in section 10.1 is the same as section 9.2. So if you didn't get it the first time, hey, here's a second chance. If you did get it the first time, then excellent. Move on with yourself and enjoy knowing. A couple of new vocab words other than center and radius and diameter and circumference and area is we're going to talk about concentric circles for a second. So concentric circles. Alrighty, so concentric circles are two circles that have the same center. Con with center. I only know Spanish, I don't know Latin. So con in Spanish is with. So those are circles with the same center. Concentric circles. We will want frame of reference. There is the interior of the circle, which is inside, and the exterior of the circle, which is outside. So you'll be reading about points or lines that are on the interior or the exterior. We talked about chords before, chords. A chord goes, the endpoints of the chord are on the circle. So there's one special chord that goes through the center, and that's the diameter. Any other chord is just a chord. It doesn't have a special name other than chord. Okay, so I'm noticing in this section they bring up area and they bring up circumference again. I am going to assume that you've got that down. If not, go back to the 9.2 video and get some help. There are 3 theorems that we're going to talk about. They're all related to each other very closely, the difference being what you know to be true and then the conclusion you can draw from that information. So I'm looking at page 441 in your book if you want to follow along there. My drawings aren't fabulous. The book looks better. There are 3 theorems there, and they're going to talk about a radius and a chord that are perpendicular. So a radius and chord that are perpendicular. Perpendicular. There we go. So the first theorem says that if a radius is perpendicular to a chord, so here's our picture, circle, if a radius is perpendicular to a chord, and the chords that they're talking about are not going to be diameters. So if a radius is perpendicular to a chord, boop, then, well, guess what? What kind of triangles are these, by the way? These are going to be congruent triangles, right? They have a right angle, they share this side, that side, so by HL they're congruent. So anyway, if a radius is perpendicular to a chord, then it bisects the chord. So we have this is congruent to that. So keep in mind, you know that the radius is perpendicular to the chord in this theorem. In the next one, you're given a little bit different information. You know that the radius bisects the chord. So if a radius of a circle bisects a chord, again, not a diameter chord, then it is perpendicular. Then it is perpendicular to the chord. Perpendicular to the chord. So keep in mind, this one we knew that the radius is perpendicular to a chord. This one we know that the radius bisects a chord. So just keep in mind what part you know versus what conclusion you're drawing. And then the last one, you could probably figure out what the last theorem is going to be. So the given information this time is if a perpendicular bisector passes through a chord, if a perpendicular bisector passes through a chord, then it also passes through the center of the circle. So this one, you know that it's a perpendicular bisector and it passes through a chord, then it's also going to pass through the center of the circle. So those are 3 theorems from this section. And yes, we are going to do some proofs. So get yourselves ready. Maybe you missed them. Maybe you're so excited that they're back. Okay, so let's draw ourselves a circle. Here's a circle. There's its center. We'll call this circle Q. And here's a chord. And I'm going to draw lines here and here, make ourselves a triangle. And then this line goes like that. And this is S, T, P. And this is R. I'm going to draw a little arrow because my pen is so fat. I can't get an R in there. And we are given circle O. Remember, this is the symbol for circle, the circle with the dot in it. So, I'm sorry, circle Q, not circle O. And we know that PR is perpendicular to ST. That's part of our given. PR is perpendicular to ST. We're going to prove that PS is congruent to PT. So PS congruent to PT. Here we go. So we know it's a circle, and we have perpendicular lines. So we know that this radius, QR, is perpendicular to ST. So we can say PR bisects ST since a radius is, I'm going to abbreviate perpendicular to a chord. So then, since we have a perpendicular line and a bisector, now this is a throwback, okay? So since PR is a perpendicular bisector to ST, then PS is congruent to PT since, well, actually I use since, because if a point is on the perpendicular bisector of a segment or line, then it is equidistant from the endpoints. Now, could you have done this a different way? Probably. You could have said that SR and TR are congruent. And then you've got PR is congruent to itself. And then you've got congruent right angles, so you could have done SAS. And then you would have had a perpendicular bisector. So then you can say by PCTC, PS is congruent to PT. That's another way of doing it. All right. Does that take you back a little bit? Back to the old days of proofs? All right. Let us deviate for a second from proofs. Let's go and work on a problem maybe with a triangle in it. So we'll do a little throwback to last chapter. So let's say that the radius of the circle is 13. Radius is 13 units, whatever those units are. And the chord is 10 units. Find the distance from PQ to center O. A little tough without a picture, so let's draw in the picture that we're given. There's O, there's PQ. So the radius is 13. In this circle, the radius is 13. So we know that from O to Q or O to P is 13 units. We know that the chord from here to here is 10. We need to find the distance from the center to PQ, so this distance here, we'll call it X. Well, this line here is perpendicular. That is the shortest distance from the point to the line, is to draw a straight perpendicular line. Any other line is going to be longer. This looks a little bit like a right triangle, doesn't it? And chords and radii that are perpendicular, we have a bisect there. So we know that this piece here is 5. Now you can use your families or you can use a Pythagorean theorem. It doesn't matter to me. But we can say 5 squared plus x squared equals 13 squared. Or you can say, hey, it's a 5, 12, 13 family, so x must equal 12. Okay. Last problem. Let's do one more proof. Can you hear my family going in and out? It's very exciting. They're so bored. Are you that bored? We've seen more Phineas and Ferb over this time period than I've ever seen in my life. Okay, here we go. We've got, it's a combination, right? With the rain and the quarantine, we're all going nuts. Poor Californians. We don't know what to do with ourselves. All right, and then we're going to draw a line from here to here, and this is A, B, C, P, Q. And we're going to be given triangle A, B, C is isosceles. And you have circle Q and circle P, so they're both circles. And BC is parallel to PQ. Oh, interesting. Parallel lines. That's like way throwback, right? All right, and we're going to prove that circle P is congruent to circle Q. Okie dokie. Here we go. Let's think about this. If we want to show that these two circles are congruent to each other, that means their radii will need to be congruent. So congruent radii. And in terms of this problem, it's going to mean that BP is congruent to CQ. That's what we're going to eventually want to show. Okay, so we know that we have an isosceles triangle. And so we can say that since triangle ABC is isosceles, we can say AB is congruent to AC. All right, and then we've got angle ABC up here. And angle P, those guys are going to be congruent to each other. So angle ABC is congruent to angle P since if parallel lines cut by a transversal, then corresponding angles are congruent. Okay. So then we've got also that angle ACB is congruent to angle ABC, because if this, then this. You could have switched these two around, that's fine. These last two sentences. Okie dokie. So then we also know that, period, angle ACB is congruent to angle Q, since if parallel lines, then corresponding angles are congruent. Could you have put that with up here? Absolutely. So now we've got all of these angles congruent. So by the transitive property, angle P is congruent to angle Q. Alrighty, so we also then can say if the base angles are congruent, then the sides are congruent. So AP is congruent to AQ, and then by subtraction, BP is congruent to CQ. Therefore, circle P is congruent to circle Q. Yeah, you could probably shorten it up a little bit by combining some of the sentences. And sure, you can rearrange the order of some of them. But just to get us back into the swing of proofs, there you go. All right, let me know if you have questions on the assignment. I will go over those on, golly, I guess Friday will be the next time I see period 6, right? No, period 6, you're tomorrow. I'm getting confused. I'll see you around. Bye.